out the chart. Okay, let's go across and check that we have the right information in the rows because that's going to help us answer the questions correctly. So, for row A, somebody tell me what did you get when the sum for n equals 5 terms? More. 31 over 32 or 0.9 something, right? Okay, good. All right, somebody else tell me the sum you got when n was equal to 50. Ashley. 1. Okay, what about when the sum for 500 terms? Also 1. What about the sum for 5,000 terms? Also 1. Okay. What about the sum for 50,000 terms? Also 1. So this is kind of crazy. Okay. The sum came out to be the same whether we were adding 50, 500, 5,000, 50,000 terms, but technically we were adding more terms to it, right? Like 50,000 terms, there would literally be 50,000 things being added together. And so we want to kind of figure out what's happening there. All right, what about in part B? Who can tell me the answer they got for 5 terms? More? Negative 11 over 32. And what was that as a decimal? Negative 0.3 something. Okay. And then what did we get for 50 terms? Michelle? Okay, so negative 0.333. Okay, what did we get for 500 terms? Ashley? Negative 0.333. Okay, what did we get for 5,000 terms? Negative 0.333, and for 50,000 terms as well? Okay. All right, so who can tell me in part C, what did the sum start off as? Lauren has started us off every time. Somebody else. Ashley gave us a couple too. What did your sum start off as in part C? Yeah, Jason. 3.875. Okay, so 3.875. And then what was your sum for 50 terms? Somebody else knew. What did you get? Yeah, got 4. Okay, what did we get for 500 terms? Danny? 4. Okay, what about 5,000 terms? 4. 50,000 terms? 4. Crazy, right? Okay, so then we get to part D. Okay. Can somebody tell me what you got for the first sum in part D for 5 terms? Chase. 62. Okay. What did you guys get for the second sum? Did you guys get, here's what I got, so in case you're a little afraid. I got 2.25 times 10 to the power of 15. Is that a small number or a big number? It's a big number, right? So it grew a lot, okay? It grew from 62 to this huge number. Is that what we saw in the previous series? No, we saw something, and then we saw it kind of like settle down at something, right? Whereas this one, we see it grow a lot. And then what happened when you tried to get the sum of 500 terms? Overflow, right? Too much to even put on the calculator. Too big a number for that calculator to don't get me wrong. There is something out there that can tell you, like a computer, what that number is. But too big for us to calculate on our calculator. So this overflowed. And then that meant this one would too, because then we would just be adding more stuff to it, and this one would too. Okay. So then what about part E? What did we get as the first sum? 15.5. Okay, and then the second sum for 500 terms, or 50 terms, sorry. Ashley? 5.62 times 10 to the 14. Yeah. Okay, and then what did you get when you tried to find the sum for 500 terms? Did you guys overflow again? Yeah, I got that too. Okay? So overflow, same thing here, same thing here. So this pattern you should have seen continue for F and G. Did you guys see that? So check your work. For the first sum for F, I got negative 22. And for the second sum, I got 7.5 times 10 to the 14th power. And then I overflowed the rest of the time. Okay. And then for part G, I got a few more sums. Okay. For part G, I got 12.86. For the first sum, I got, hold on, let me write it before I tell you what it was. 7,063,119.85 for my second sum. Then I got 1.17 times 10 to the 63rd power. Process for a minute how big that number is, right? Move the decimal 63 places. Okay? Just so you move it. Okay? And then I got overflow and the same thing here. you looked at a bunch of different geometric series, okay, we would say that some of these series converged and some of them diverged, okay? So to converge means to settle on a given value. To diverge means to continue to keep growing, okay? So which series up here would you say are convergent series? Okay, they settled to one specific value. Bishop? Good. A, B, and C. Okay. And then we would call the other series, D, E, F, and G, the ones that kept growing and then eventually overflowed. Those would be divergent. They didn't settle on a specific value, right? They just kept growing. Okay, so D, E, F, and G would be divergent. Are we comfortable with the words convergent and divergent? Are we comfortable with the idea that we can add more terms to something, but it still settles at a certain value? Okay. We'll see a little bit more about how that happens. Okay. So if we look at the next questions it asks us, so number 3, write down your sum formula. So go back in your notes from yesterday if you have to. And remember what that sum formula was that you were putting into the calculator over and over again. Okay. And go ahead and write that down. So it should look like this. Okay. So the first question I want to know about that sum, so you have the formula in front of you, right? So I want you to focus on this part first. If we just had the r to the n, okay, so looking at number 4, it says, what's the limit as n goes to infinity of r to the nth power? Okay? So remember what that means. We used the limit, right, as end behavior, like as this keeps getting bigger, as it's going towards infinity, what's happening to this function? And sometimes the end behavior of our functions shot off, right, the oblique asymptotes, so we had to have some line. But other times they settled down to one number. Did they ever actually reach that number? No, but did they get infinitely closer to it without ever crossing it, right? Like cutting things in half. If you continue to cut a number in half, when will it reach 0? Technically never, right? But eventually it'll be 0.00000000000 something, and it's going to be so close to 0 that you would probably just call it 0, right? So that's what was happening to our sum. You were adding more terms every time, but the terms you were adding were so ridiculously small that they weren't changing the overall sum when we looked at it. Does that make sense to everybody? Okay? So, here what I'm saying, as I make n bigger and bigger and bigger, what happens to this calculation? Okay? And we're only looking for the series that were convergent. Okay? So let's look back at the ones that were convergent. Look at A, B, and C. Okay? What is true about the r value in A, B, and C? And it's not true about the r value in D, E, F, and G. Kenny? Good. They're all less than 1. So, but then this one's less than 1 too. So we have to say it a little bit differently. You have the exact right idea. But see, technically F has an r that's less than 1, but it doesn't fall in the category. Jason? Good. The absolute value of the ratio is less than 1, right? So take off the plus or minus. Just look at the number part of it. If that part's less than 1, we were in convergent world, right? And if that part was bigger than 1, we were diverging. Okay? So I'm asking you guys to look just at the ones that were converging, which means the r right here, its absolute value is less than 1. So think of a fraction between 0 and 1 to help us wrap our heads around this, like a half. Okay? What's going to happen if you start raising the number 1/2 to really big powers? So like, what's 1/2 squared? 1/4. What's 1/2 to the 3rd power? 1/8. What's 1/2 to the 5th power? 1/32. Okay? What's 1/2 to the 6th power? 1/64. To the 7th power, 1/128. What's going to happen if you make this exponent go towards infinity? What's going to happen if you put the biggest exponent you can on 1/2? It's getting smaller. How small is it getting is the question. Samantha? almost close to 0, but not actually, right? So if you put it in, your calculator might eventually tell you 0. Though we know mathematically it doesn't technically come out to 0. At that point, it's 0.0000000, something that people would call 0, right? Okay. So what happens? The limit goes to 0. Okay. It gets closer and closer and closer to being the number 0. Just kind of like an asymptote would act on a graph. But r to the nth power doesn't exist alone in the formula you wrote down. Look back at the formula you wrote for s sub n. Rn isn't just sitting there alone, so it's not like the sum comes out to be 0. But this part of it, if you put big exponents on ratios that are smaller than 1, or whose absolute value is smaller than 1, this part of it is going to start becoming like the number 0. Right? So here's the next question. What is the limit as n goes to infinity of 1 minus r to the n? Okay. So what did we say happens to r to the n as you make n go towards infinity? The exponent gets really big, and this part becomes what? 0, essentially. That's its limit. So what's going to happen when you have 1 minus 0? What number are you basically going to be getting? 1. So the limit of this is going to be 1. Is that okay with everyone? So now let's take the whole formula and look at it. If we're looking at this big formula, and again, we're saying that we're in convergent series world. Okay, so this is just for the ones that were convergent. If you take the formula and your r value, its absolute value is less than 1, and you start making that exponent bigger and bigger and bigger, you guys already said this part becomes like 0. And then you told me the 1 minus 0 basically becomes 1. Are there any other n's on anything in the problem? No. So it's basically just this part that's affected by that, right? Which means our formula gets changed to this idea. There's our a1. The numerator is basically just a 1 now. I don't need to do 1 minus r to the nth power because that's getting so ridiculously small, and 1 minus that is just 1. And I still have this in the denominator. Okay? So here is our conclusion. Can you find the sum of an infinite geometric series? So let's go back. What if I said don't stop anywhere, just keep adding and adding and adding forever? Would G have a sum? Bigger, 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 overflow, overflow, overflow. Does it have a place it stops at? No. If you keep adding stuff forever, you're just going to get bigger stuff, right? And that is true for G, F, E, and D. However, look at the pattern that we saw, for example, in A, right? So for the first answer in A, it was like 0.9 something, right? And then for 50 terms, it was 1. And then for 500 terms, it was 1. And then for 5,000 terms, it was 1. And for 50,000 terms, it was 1. And for 500,000 terms, what's my sum going to be? 1. And for 5 million terms, what's my sum going to be? 1. So for infinitely many terms, what's my sum going to be? 1. So weird, right? You can add up something that's infinite. Only in certain circumstances, though, right? Okay? So what are the circumstances in which we can add up? Can we add up an infinite arithmetic series? No. Okay? The terms are changing too much because you're always adding or subtracting an amount on there, which is going to make it change that much every time. Okay? Can we add up an infinite geometric series? Sometimes, right? What would be the condition that you would tell somebody? You can actually add up an infinite series if the series is geometric and if what? If it's convergent. And what did we say decides if it's convergent or not? Ashley?
If the absolute value is
Good. So we have a new formula. Okay, we can add up an infinite geometric series, and this is the formula. So more simply, people tend to write it like this. It's a lot simpler than the regular sum formula. It's the first term divided by 1 minus the ratio. Okay, why is it simpler? Because all this went towards 0, right? So it kind of took out all of those options that we had to calculate. But you can't use this all the time. Can you do this for every geometric series? No, only the ones that are convergent. So it would have to be geometric and it would have to be convergent to add up infinitely many things, which is crazy when you say it, right? So we want to tell people you can use this formula to add up an infinite geometric series, but only when it's convergent. You're usually not going to see people write the word convergent. You will in higher level, which is why we do it in here, because that's you guys are on a path of kind of we're doing some pre-calc at the same time kind of stuff. But you would see this more likely. The absolute value of r needs to be less than 1. So those are all the things we figured out, right? Some of them stay at a number, some of them change. Only the convergent ones stay at the number, which means you could add an infinite number of things because it's not changing anymore, and this is the formula we would use. Okay? Just less than 1. Actually, if the ratio is 1 or 0, we don't include those as geometric series, because if the ratio is 0, you just have 0 the whole time. So it's actually a constant function. If the ratio is 1, think about this. If the ratio is 1, 1 raised to any power is 1. So again, you just have a constant function. So we don't technically consider ratios of 0 or 1 in these rules because we wouldn't consider those geometric sequences or series because they'd really be constant. Okay? All right. Are we okay with the formula? All right. So now to use all the stuff that you guys have learned. So let's go ahead, since we're talking about the infinite now, and look at if we can do this. So go ahead with your group for a minute. Look at each of the series. My advice to you, well, let me ask you guys. If you're trying to decide if it converges or diverges, what piece of information would you want to know about the sequence or series? Ashley knows. Okay? The ratio. Yeah. Okay? So I would look for the ratio, okay, and think of different ways you can figure that out, of these three sequences or series to decide if they converge or diverge. Okay? All right, so take a minute with your group, figure it out. If they do converge, you should be able to use the formula we just solved to find the sum. Okay? Okay, a few of us are done, so let's talk about this. All right, so first series, okay, starts with -5, then I see -5/2, -5/4, -5/8. What is the ratio in this geometric series? Michael? 1/2. Good. Therefore, is this geometric series going to be convergent or divergent? Convergent, okay? Meaning I can find the sum. And see the ... at the end? So they're telling us it keeps going. So if anybody asks you to find the sum of something and it looks like that, don't come say, Miss Dahl, they didn't give me the last term, so I don't know where to stop. They're saying they want you to find the sum of something that doesn't stop, and your answer is either going to be a number because you can find the sum because it converges because it has this ratio less than 1, or your answer is going to be cannot find the sum, right, because it diverges. That could happen. So in this case, we can find the sum. So our sum is going to be our first term, which was -5, divided by 1 minus 1/2. So that's -5/1/2. Okay. If you do your fraction math correctly, this should be -10. Okay. Okay, second series. I see 1/4, and then -3/8, and then +9/16, and then -27/32. What is the common ratio in this geometric series? Bishop. 3/2. Are we good with that? How about a negative with it? Yeah. Okay, good. So, despite negative or positive, though, right? I look at the number part of it, the absolute value of the ratio. Is it less than 1? No. Even though it's a fraction, it's not less than 1, right? So this series diverges. So no sum because it diverges. All right. C. Okay. What is the ratio? You can tell just by looking at it. We talked about this yesterday. What is the ratio? Lauren? 0.8. Do you guys see that in the formula, the ratio is always the part being raised to the power. So the ratio here is 0.8. So is our series convergent or divergent? convergent, which means we can find an infinite sum. Notice the little infinity on top of the sigma. Don't come bring your test to me and be like, Miss Dahl, you misprint, okay? You forgot to put the number where you wanted me to stop the series. I didn't. I put the infinity symbol, which means your answer is either a number, because this series converges and you can find an infinite sum, or your answer is there is no sum because it diverges. Okay? So in this case, we look at the ratio. It does converge. There is a sum. So our sum is going to be found by taking the first term. Now, the first term, according to my sigma up there, means I'm going to take their formula and plug in what? 0. And when I plug 0 into that formula, what am I going to get? 1. Okay, 0.8 to the 0 power will give me 1. Remember, anything to the 0 power is 1. Okay, over 1 minus my ratio, so 1 minus 0.8, which gives me 1 over 0.2. Don't leave decimals and fractions. No one's going to give you an answer like this. Okay? So a little piece of advice, if you don't have a calculator and you're simplifying something like this, if you want the decimal to move, what should I multiply by? 10. If I multiply by 10 in the denominator, then I need to multiply by 10 in the numerator. 10 over 2 is 5. Okay? Are we okay with this? Yeah, Michelle. I plugged 0 in because sigma said n equals 0 first. So I plugged 0 into there, and anything to the 0 power is just 1, and it's not being multiplied by anything. So we just got 1 that way. Okay. Other questions? Okay, other type of question we could be asked about these infinite series. Okay, so here's one that tells you the sum is 10. So they tell you the sum. You're not looking for the sum. And they tell you the first term is 4, and they ask you the common ratio. What should I do? Any? Okay, sure. So infinite geometric series means my sum formula looks like this. Okay, so my sum is 10. My first term is 4. I need to find the ratio. Everything kind of fits. Okay, it's pretty straightforward if you know the formula and what you're looking for. How do I solve a problem that has this denominator of like 1 minus r? Savannah? Okay, I can divide 4 by each side. I'm actually going to do something else first because I don't want to deal with the fraction yet. Because the r is in the denominator. So what are we going to do when the variable is in the denominator like this? What can be helpful to us? I see Lauren and Ashley. I'm just making other people. Yeah, good. Good. Okay, so if I want to isolate the variable, I first want it out of the denominator. So I'm going to choose to multiply by 1 minus r on both sides. So we saw this with our rational functions a couple units ago. So on this side, I just get 4, and on this side, I would get 10 minus 10r. And this is going to help in my isolating the variable. So now I'm going to subtract 10 from both sides. I'm going to get negative 10r equals negative 6. I'll divide by negative 10. And so r is equal to 6 over 10, which reduced is 3 over 5. Any questions about that? You just got to remember how to solve. All right, last question is a little more interesting. So, you know those never-ending, non-repeating decimals? Okay, are they rational or irrational numbers? Irrational if they're never-ending, non-repeating, right? What if they're never-ending but they're repeating? They're rational numbers. They fall into the definition of rational numbers means you can write the number as a ratio. What is a ratio? A fraction. Okay? And some of these you guys know by heart. 0.3 repeating. What fraction is that? 1/3. You guys are good at that, right? But like 0.18 repeating. Who knows? Okay? Actually, the idea that we just learned can figure it out for us. So, first of all, notice what it says. It says if you have 0.18 repeating, that's really like having a geometric series, because it's really like you have this, 0.18, and then you're adding on to that 0.0018, okay? And then you're adding on to that 0.000018, etc. forever, okay? So first of all, before we even say it's geometric, are we good with calling this an infinite series? Okay, that decimal can be an infinite series. Okay? Then the question is, how do we classify it as an infinite geometric series? There has to be a common ratio, right? Meaning if my first term is 0.18 then my second term, this 0.0018, was made by 0.18 times some ratio. What would be the ratio in this case? The number doesn't need to change, so I just want 18 times 1, because I just want 18. But how do we get 4 decimal places instead of 2? Yeah. Good, times 10 to the negative second, or 0.01. Is it okay if I just do that? All right? Because when you multiply decimals together, remember what you do. You multiply them like normal numbers, right? And then you just count how many places are after the decimal, and you do that thing. So I just want 18, so 18 times 1 is 18, but I need 4 numbers after the decimal, and this achieves that. Okay? So this one would be 0.18 times 0.0001, but that's not really a new number. That's really just 0.01 being squared. Okay? So now are you okay with me saying this isn't just a series that's infinite? This is a geometric series that's infinite. There is a common ratio between the terms that I could find. Okay? In this geometric series, what is our first term? 0.18. What is our ratio? There. Good. 0.01. Okay. So can we write this as a fraction? Sure, I have a formula that adds this up for me as a fraction, right? It says the sum of the infinite series is the first term divided by 1 minus the ratio, okay? Which gives me, and you guys all want to pick up a calculator and do it, I'm sure, but based on how we simplified the other problem, it's not that bad. If I have 0.18 over 0.99, I want it as a fraction, but I don't want decimals in my fraction, what do I need to multiply this denominator by to move this decimal 2 spaces? 100. And then I need to multiply the numerator by 100 at the same time. So 0.18 over 0.99 is the same thing as 18 over 99. I think 9. Take out your calculator, put in 2 divided by 11. Tell me if we get 0.18 repeating. Yeah? Oh, yeah, mind blown. Okay? Crazy. This math stuff actually does some stuff with all these relationships. Who would have thought? Okay. So, pretty cool. Are we good with infinite geometric series stuff? So we understand the formula. We understand when we can use it, about the ratio and those kinds of things. Okay, so let's go back and practice a little bit with the formula that we used yesterday. So I know I didn't go in order. Okay. So why are these problems not infinite problems? How do you know just by looking at them? It says find the sum of the geometric series. Kenny? Good. In both, there's an endpoint. In the first example, there's a number at the end that we are stopping at, and at the second one, it says add up the terms from the 0 to the 11th term. That is a specific set that we are adding together that's not infinite. So in these problems, are we using the A1 over 1 minus R? No. We're using the more complicated sum formula, right? The S sub n equals A1 times 1 minus R to the nth power. Okay? In order to use this formula, what are the 2 pieces of information that I need to pull out? Okay, or 3 pieces technically, that I need to know in order to get the sum. Yeah. A1, R, and N. Okay? So look at the first formula, okay, or the first series. Do you know A1? Yes. Okay, so we know A1 is 4. What is R? 3. Times by 3 over 10. I agree with that. What is N? Sucky, huh? Okay, so we need to know what 2,916 is. Is it the 10th term, the 12th term? I don't know. What could we use to help us figure that out? We had to do the same thing with arithmetic sequences in series. Good. The explicit. Take a break from the sum formula for a minute, right? Go look at the rule and see if that ends up being the 10th term, the 12th term, whatever it is. So if I go back to my rule for a minute that looked like this, okay, I know that my first term is 4. I know that my ratio is 3. So here's how the rule looks in general. So if they want to find the 10th term, they plug in 10. Okay? I already know what I'm supposed to get. I'm supposed to get 2,916. So the question is, how do I solve this equation for n? Well, the first thing I do is I get rid of the thing that's not part of the exponent, the 4. I should divide both sides by 4. And so when I do that, 729, somebody check for me, okay? Yeah? Okay. Okay, so then I have this. Now we're going to learn something. We have not learned anything that removes a variable from an exponent. And we cannot isolate a variable when it's in an exponent. Okay? But if we're talking sequences and series, should n be anything crazy like 4.2? Is it the 4.2nd term that's going to add up? No, it's either 1, 2, 3, 4, 5. It's a whole number that we're looking for here, okay? So that means 729 should be 3 to some power. So use your calculators real quick and try some different powers of 3 and tell me, 729 is 3 to the what power? Yeah? 6th power? So if 3 to the 6th power is supposed to equal 3 to the n minus 1 power, these things must be equal to each other, right? Like 3 to the 5th power doesn't equal 3 to the 8th power, people. Okay? They got to have the same power on the 3's if they're going to be equal. So that means this power must be equal to 6. So n must equal 7. Okay? So this means I'm adding up 7 terms. A 7 should go there. Okay? We practiced putting into the calculator yesterday, so for the sake of time and to show you some different things on Canvas, I'll just tell you this should turn out to be 4,372. All right, so looking at part B, okay, if we look at part B, same idea, but sigma notation, which some of you don't like, so I just want to make sure that we're okay with it. So we said before we need the first term, and we need the ratio, and we need the n. So first term, how do we get it from this sigma notation? I see 4 nice hands, but they've all helped me earlier today. Okay. Good. We're going to plug in 0. And then you're like, what? It says A1. Well, sigma is saying the first term is made by plugging in 0. So follow the directions and plug in 0. So we plug in 0. Negative 1.5 to the 0 power is just 1. Okay. And then 1 times 3 would be 3. So first term is 3. What is our ratio? Savannah. Good. Negative 1.5. Hopefully we're at a place where we can get that just by looking at it, because that's the exponential part of it. That's the base. How many terms are we adding together? What is the n here? Ashley? No. It's a little bit tricky. I know. Michelle? 12. So we talked about this before with sigma. When somebody gave us a sigma notation, it's really easy for us when they say add from 1 to 10. That's like being assigned numbers 1 through 10 for homework. That is 10 problems, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? When they say do problems 3 through 10, how many problems are you doing? 8 problems. Okay? Because when you do 10 minus 3, that counts if you are already done at 3. How many more do you have to get to 10, right? So from 3, meaning 3 is already done, it takes 7 more to get to 10. But subtraction doesn't count both endpoints. But when we're using it, we're using both numbers, right? We're using the 3, we're using the 10. So when they say from 0 to 11, 11 minus 0 is 11, but that didn't account for actually plugging in 0. That only counted moving forward from 0 to 11. So we have to add 1 back to get 12. Remember how we talked about this with arithmetic sequences and series? Okay. So we actually have 12 terms here. Right? So in our sum formula, we would be adding up 12 items, where the first term is 3, 1 minus negative 1.5 to the 12th power. Be really careful when we put this into the calculator. Right? And if you do so, and you do so correctly, you should get negative 154.5. skip and do one more. We're not going to do all of them, but I want to do the same. You know how we just did the repeating decimal? How we learned how you could actually look at a repeating decimal now and know what fraction it is, even if it's something crazy like 2/11. Okay? You can use that same idea with just numbers that repeat. Okay? So, for example, we'll just do one of these. Say we're doing the 7,777. Okay? And we wanted to write that as a sum of a geometric series. Okay? So basically you have 7 plus 70 plus 700 plus 7,000. Is that fair? Okay, that would make 7,777. Okay. So basically our first term is 7 with what ratio? What's your ratio between the terms here? 10, right? Times 10 gets you from one to the other. This one's not infinite. How many terms are we adding up? 4, right? There's a limited amount of things, 4 things. So the way that you could write this as a geometric sum, we could write it like this. And I just wanted to use this opportunity to remind you guys how to put together summation notation, because I know you guys really didn't like it the first time we looked at it, so I want to remind you. So you need your sigma symbol. Okay. What's my rule going to be? I have my first term in my ratio, so I should be able to write my rule. It says A1 times R to the n minus 1 power, right? So what's my A1? 7 times R to the power of n minus 1. Okay. Then I just need to tell them the starting and the stopping point for n. When we write our own sigma notation, we are saying that this rule starts when you plug in 1, right? That's what we're basing our rule off of. So every time we write sigma notation, what should we start our n value at? 1, because that's how we're basing our rule calculation. They can change it and write the rule differently. But if we're writing the rule like this, we would base it off of 1. And then where do we want to start? First term, second term, third term, fourth term. Okay. So we're going to stop by when they plug in 4. Right? And this would be how you would write it in sigma notation. All right. So you should be able to do homework 2 tonight. Okay.